All right. So sorry I wasn't here last week. I hope the online lectures were okay. If you guys have any questions about classification, please reach out. So as you know, this Friday you have an exam. So I posted a practice midterm for you to work on. And then I won't be posting the classification homework until Friday so that you're not distracted. And then that classification homework will be due a week from Friday. So you'll have a little bit of a break to focus on reviewing units 1 through 4, preparation for the midterm, and then get back to material. And we are gonna start with unit 6 now, because basically what's gonna happen is there's gonna be a sort of a slight delay from the midterm week, but then some of the later units are a little bit longer, so it's going to take us more than a week to get through them, and then eventually we'll sync up. So there is sort of a plan to all this. But anyway, we're going to move on to Unit 6, Optimization and Gradient Descent. So just sort of to motivate us for this unit, we're going to recall one of the more important equations from last time, which was binary logistic regression, where we had 0, 1 labels, and we said that to design the weight vector W that maximize the likelihood or minimize the negative log likelihood was given by this problem here. So we have sum over our training samples, we have these scores, ZI for the ith training sample, we have our labels. And this is what we want to do. We want to find the W vector that minimizes this. And as we saw, there's no way to do this on paper. You can't just write down the equation for this WML. However, as we'll learn in this unit, this is called a convex function. That means we can minimize it in a tractable way numerically. And so this unit is going to focus on how we do that numerical optimization, and the ideas, of course, go beyond just this particular objective here. We actually can use this for a lot of things. Will be a lot of optimization problems within machine learning will follow the same approach. Okay, so how did we do this before? We used this logistic regression method in scikit-learn. So we instantiated this logreg object. Then we scaled our features, and we did logreg.fit. When we do that internally, there's an algorithm that's going to be run to solve this problem. And we're going to try to develop algorithms like that ourselves in this unit so that we understand what's happening under the hood. Okay, so yes?
The C is for recognition?
The C. Oh, yeah. Right. So, so I think in the last unit, one of the things that you learned was that when you, so by default in sklearn, this method includes L2 regularization. The reason for that is if you don't have it and you apply it to a linearly separable data set, the weights will actually grow to infinity. And we don't want that to happen. So we just have a little bit of L2 regularization. And as we also know, if you have a lot of L2 regularization, that squeezes your coefficients towards the origin, which biases them. So what you want to do is you want to use a very small alpha, which is the weight. And when we work with this object, it actually uses the inverse weight. So you want that C to be really large. And what that will do is it will keep everything finite, but it won't bias you too much. So another approach that would maybe be more involved, more correct, is to do a grid search over many different values of C and look for cross-validation, probability of error, and so on. And you could probably come up with a better value of C, but if you want to just run this without doing that quickly, the recommendation usually is to choose a large value of C so that you are sure you're not biased. And yeah, that's sort of the recommended approach. My guess is that I can't remember exactly what the default value of C is, but there is some default value. It might be large. Hopefully it is, because that would hopefully make sense. Okay, all right. Any questions here? All right, great. So to understand optimization, we have to sort of start at the beginning. And we're going to focus on optimization in the case that we can use gradients. And so this idea of gradients is actually something that we've used several times before. We talked about it in Unit 1, talked about it in Unit 2. And so let's review a few of these things before diving in a little bit more deeply. So our objective here is to find the minimizer, W hat, some cost J. That's the W's that minimize J. And so we saw several times a gradient is really useful because assuming that this J is differentiable, in like one dimension, you know that the minima occurs, let's say, at the bottom of this bowl, and at the bottom of that bowl, the slope is 0. And when you extend this to 2 dimensions, sorry, it's tough to draw it, you can look in 2 directions and find the slope is 0 in both those directions. And when you think about what is that pair of slopes in the 2 directions, that is what we call the gradient. So we'll be getting into some details, but basically, I think this is also a picture we've seen before. So in this case, the little arrows are showing us the value of the gradient at every one of these grid points. So like when you see the arrow pointing this way, that means this is uphill. The length of the arrow tells you how steep it is uphill, and the direction of the arrow tells you the direction to go in to move straight uphill. So you can see, like, if you want to move uphill, you'd actually go curve around like this. And then this is where all the gradient arrows are pointing. This would be the peak, somewhere over here, and then somewhere over here would be the minimum, the trough. So all the negative gradients would be pointing down this way. And so one way to figure out where this trough would be is to try to solve for the 0 gradient position. If you do that, you could find either this point or this point, but maybe if you have a function that is only curving up and you do that, then you would find you would only get this point. And that's what's going to happen, at least with our with this cost function. It is sort of curving up everywhere. It's convex, and it's going to give us the solution we want. So essentially, we care about gradients because one way to minimize is we look for the vector that zeros the gradient, the W that zeros the gradient, and that is the minimizer. Okay, as we'll see later today, we can convince ourselves that this is going to give us the direction and the direction of maximum increase and the slope at a given point W. Just sort of as a caution, we can only do this, we can only compute the gradient if the function is differentiable. We'll assume that this is the case, but we should be aware that there are interesting cases where this doesn't happen. For example, if you use L1 regularization, right? Because L1, if you think about it, it's like these absolute value function, which is not differentiable at the origin. So if you were using L1, you can't actually use this stuff. You actually have to take a different approach, which we're not going to get into in this course because it's a bit more involved. So for the purposes of this course, we're going to focus on differentiable losses or cost functions and setting the gradient to 0. And we'll also talk about how we can, later today, we'll talk about how we can use the gradient to linearly approximate functions, which is going to be super important for us. Okay, so that's sort of just an intro to gradients. Now let's get into some of the details. In all cases, we're going to have a scalar valued function that we're trying to minimize. So it's important that this is just returning a scalar, because if it's returning like 2 things, it's not really clear what you mean when you want to minimize it. You know, maybe one gets bigger, the other gets smaller. So we always have a cost J that just returns a single output. But there could be many inputs to this. So for example, in this case, here, this is our cost that we want to minimize, but this has as many inputs as there are coefficients in W, right? So in general, D plus 1, D features plus 1 more here. So in that case, let's just suppose that W has coefficients W1 through WD. Then we've seen before that the way you define the gradient, in this case, that's what the upside down triangle tells you. The gradient of J is a vector, where in the first element, that's the partial derivative with respect to W1, the next element, partial derivative with respect to W2, and so on, all the way to the end. Okay, so I think we've seen this before. But we can also do the same thing if the input is a matrix. Can anyone remind me of when we might have a function where we have to optimize over a matrix? I can think of a couple. When have we seen matrix value parameters?
Vector value targets.
Vector valued what?
Targets.
Targets, yes, right. So in linear regression with vector value targets, we had a whole matrix. What about in classification? When did we see a vector value W in classification? Maybe you guys didn't watch the videos yet. So multinomial logistic regression, right? That's where you have, again, vector value targets. Because you have k greater than 2 classes and you one-hot code the different classes, and now you have a vector of 0, 1s, and you're trying to predict that vector. So that would be another case where you have a matrix W. So in both those cases, you might want to define what is the gradient. In this case, the gradient is it's the matrix of partial derivatives of J with respect to all the individual coefficients in W. Right, so the top left would be W11, bottom would be WD1, bottom right, WDK, assuming you have D going this way and K going this way and so on. So the key point here is that the gradient always has the same dimensions as the input. So if you take the gradient with respect to vector W, then the gradient will be something the same size as W. Or if you're taking it with respect to a matrix W, this has the same size as your matrix W. Okay. You can think of a gradient with respect to a scalar as well. That's just going to be the derivative, the simple scalar derivative. Okay, all right, so we're good on gradient definitions? Okay, so let's just look at some concrete examples, make sure we understand this. So maybe I have this function J of 2 coefficients W1 and W2, and this is just a simple function that we can work with. So if I want to compute the gradient vector, then what I have to do is I have to look at the partial derivative of J with respect to W1. So that's pretty easy to do from inspection, right? What's the partial derivative of this with respect to W1? It should be very easy, right? 2W1 plus 2 times W2 cubed, right? So that's what this is. Or we could take the partial derivative with respect to W2, in which case this goes away, and then we get 2W1 times 3 times W2 squared. So that. Okay, and then once we have these individual partial derivatives, we just pack them into a vector, and that's our gradient. Right? Simple as that. So, so here's a little piece of code that does this, and you can see actually it's going to return 2 different things. It's going to return not only the gradient vector, but also the value of the cost, J itself, this thing. And that's because almost always in machine learning, whenever you're computing the gradient, it's also useful to compute the value of the cost as well, because let's say you're descending the cost by taking gradient steps. It's nice to know the value of the cost too, to make sure that it is in fact decreasing, and to see is it sort of like is getting to the point where it's not really changing much at all. So almost always when you write a function to compute the gradient, you compute not only the gradient, but the cost itself. And so that's what we're doing here. So once this is a little function here, it just basically, each of those lines is computed, and then the gradient is packing those 2 things into this vector, NumPy array. And then here's a couple lines of code that evaluate it. Here we're coming up with a particular set of coefficients, 2 and 4. We're plugging those coefficients into our gradient function, and out comes both the cost and the gradient. We can print it, cost is 260, gradient is that vector there. Okay, as always, we're going to work in NumPy, so here the gradient is a NumPy array, as we'd expect. All right, so that's one example. Here's another example. It's a little bit more complicated, but it's a little bit more like the sort of stuff we would see in practice. So here we have a cost that depends on a number of data points, xi and yi. And if you look at it, you can see a sort of familiar structure. Here's the target. You can think of this as the approximation. y hat I at some approximation to that target. And then we have a squared, sum of squares, RSS loss. What's a little different is we're using sort of a strange model here rather than linear or polynomial. This is actually an exponential model. You have to figure out these two coefficients, a and b. But once you have those, this y hat I is just, you compute it this way, right? So we're fitting an exponential model to our data. We have two coefficients to compute, a and b. So in terms of doing this, our approach is to try to find the location w where the gradient vector goes to 0. So to do that, we have to at least be able to compute the gradients themselves. So how do we do that? Well, we just compute the partial derivatives, dj dA, dj dB, and we pack them together into the gradient vector. So let's just take a look at this. How do we do dj dA? This is just sort of repeated chain rule. So, okay, so the first thing is if you want to do dj dA, you're going to slide that through this summation, and now you have to work on this object here. So by the chain rule, you're going to have 2 times the interior times the derivative of this with respect to a, right? And important thing to see there is dDA of AE minus B xi is going to be just E minus B xi, right? And so that's how we get this expression. So here's the 2 came down and it canceled the 1/2. And then we have this thing. And then we have the gradient of this, which is here. Similarly, to do dj dB, we have to apply dj dB to this. And now everything's similar except finally when we come to this point and we need to take the gradient of this with respect to B, it's a little bit more complicated. We have dj dB of AE minus B xi. So here, A is just like a scale factor, so that comes out. And then we need to do ddB of this. Anybody remember what that is? It's this whole thing times ddB of the numerator, right, which is minus xi. So it's minus xi this. Okay, so that basically, the minus here cancels the minus here, and then that's what gives us that term over there. And now we have our 2 partial derivatives. Okay, so, and finally we just pack those together into these 2 terms, and that's our gradient vector. Okay, so that's what this code does. Now there is something, when you write code like this, it is really important to try to be efficient in how you write your code. You don't want to have the code compute something that's a bit expensive to compute more than once if you can just compute it once and then store the result. The reason why this is important because this sort of gradient code ends up being run maybe thousands and thousands of times, and so you want to be sure that every time you compute it, it's efficient. So when we look at this, do you see how we, what sort of things would we not want to compute more than once?
The exponential.
The exponential, yes, that's one thing. What else? What about this whole thing, right? If I can compute that whole thing, then I can use it twice. Okay, so that's sort of the goal. The code, it's not perfect because it's computing this exponential twice. So I think for next semester, I'm going to change the code a little bit to get rid of that. But you can see that it is computing this quantity. That's this thing. It's computing that once, defining it as y air. And then it's going to use that when it computes the cost. It's going to just take basically the RSS of that y air. So it's going to take y air. So y air actually is going to be a vector. So let's look at this. So remember that y is a vector across all our training samples. X is a vector, but a and b are scalars. So NumPy is smart enough to know how to do some of this stuff. It can multiply a scalar times a vector, and it's going to do that by applying the scalar to each one of the quantities in the vector. And then the np.exp is going to take a vector in and it's going to exponentiate every term in that vector to give you a vector out. And then that vector is going to be multiplied by the scalar, and then the minus is going to be a subtraction of two vectors. It's smart like that. So finally, y air is a vector. Now when I want to compute this, we can do y air squared. So that square is going to square every term in the vector. And now I can just do sum like this, sum over that vector, and then 0.5. Okay. Now you can see that to compute this quantity, I can take this whole vector and multiply that pointwise by this vector. And again, NumPy is smart enough. If you have one vector and then another vector of the same dimensions and you do this star, it does a pointwise multiplication between all the respective terms in those vectors. And then we can just sum it up like this. And similarly here, we have this vector times this vector times this vector over here. Sum that up according to this. So that's how NumPy is doing this. And as we'll see, it's important to understand some of this, some of what NumPy is doing under the hood, because as we'll see, we'll want to do some slightly more complicated things in just a couple slides. So anyway, once we have these two scalars, we can pack them together into a NumPy array. Now this is a just a vector with two elements, and we can return the cost in that vector. So to use this little function, we're generating some random data. We are generating some numbers for W, 1 and 2, for no reason, just pick those numbers. And then we can plug in our data and our W vector, and we can evaluate this and the cost itself, and we get this stuff. Okay, just to verify that things are working, just with some kind of random numbers. Okay, so this is a second concrete example. Is everybody getting the hang of what gradients are and how we compute them? Yeah.
Could you remind me what part of that code did the pointwise multiplication?
So any.
Double, sorry.
Oh, sorry. Yeah. So this is to the power 2, and then all these operations are all doing. They're all smart in how they're doing things. So. Let's see, so like this, which one should we look at? So this one is going to subtract a vector from another vector. So that would be a pointwise minus. And then over here, this is going to be a vector. This is also going to be a vector, so this is going to be a pointwise multiplication. Right? This is going to be scalar times a vector. But then this whole thing is a vector that's pointwise times this vector.
So it just does automatically?
Yes, exactly. Yeah, so there are some rules, and there's a nice document. Link will be coming up in just a moment. We'll see this, but yeah, it's pretty smart as to how it handles different dimensions, as long as the dimensions are compatible. Now, if you give it like two vectors of different dimensions and you say multiply them, it's going to throw an error because we don't really know how to do that, right? And in fact, you might want to do something like column times row to get a matrix, but we're going to have to learn how to tell NumPy to do that, because if you just give it these two quantities, it's not going to really know what to do with them. So we'll see that coming up in a few slides. Okay, all right. So let's move on to first order approximation. So, so this slide, just before class, I was trying to make the picture on the slide better. So if your slide deck looks a little different, it's just probably the picture that changed. But basically, this is the idea here. We want to come up with a nice way to approximate scalar input functions by linear functions, which are just like lines or planes or something like that. So we're going to look at this first with scalars, later with vectors, and then later with matrices. So this is the easy the easy part where we have a J that takes in a scalar input W. So we can make nice, one-dimensional pictures of this to visualize things. So let's think back to maybe some of the calculus courses you took where you learned about the Taylor series of a differentiable function. So if I have a function of variable w, and I want to take a Taylor series around the point w naught, it goes like this. You take j evaluated w naught, and then you take the derivative evaluated w naught, and now you take the difference between this reference point and the w you're computing it at. And there's a lot of other terms, right? There's like a 1/2 second derivative, and so on. And then you look at like w minus w naught squared, and there's a cube and a quadratic and so on. It goes up to infinity. But we're gonna say like, okay, all that stuff, starting from the second term and third, we're gonna collapse all that down into one little thing here, where there's this is called the big O. How many of you guys have heard of big O notation, little o notation? Right. So this is sort of a way of kind of, when you have a really complicated expression and you just want to summarize like how it basically works, you can use this big O. So it goes like this. There's kind of two ways in which people use this. Sometimes they use it where the argument of the function is getting really small, going to 0. Sometimes they use it where the argument is going to infinity. For us, we're going to focus on the case where the argument is going to 0. So in other words, we're saying that all these other terms in the Taylor series can be thought of as quadratic in the worst case. So in other words, this is what this means. So this w minus w naught is sort of like how far we're deviating from the reference point, right? And now notice that this is a quadratic function in that deviation. Let's think about when you have a quadratic function. Let me write it like this. Imagine that this is small. And by small, let's just say it's less than 1. So if you take, let's say, the number 0.1, and you square it, what happens to it? It gets smaller, right? If you cube it, what happens to it? Even smaller, right? So like 0.1 is smaller than 0.1 squared, is smaller than 0.01 cubed. And so when we think about this function in terms of, there's this approximation in terms of deviations from the reference point, and I think, but the cubic term and the quadratic term, those things are just smaller and smaller. Oh, I wrote it, sorry, I have these, I did this exactly wrong. So there should be did this wrong on many levels. Okay. All right, so what I wanted to do is cube and so on. So it's all this stuff. You can say it's going to be dominated by this term, right? We have just in case it's not clear, we have like 0.14 and so on. So when we consider all these terms individually, you can say, you know what, the one that really matters most is the quadratic term. So that's sort of what we're saying here. This sum of all these terms in the Taylor series here is really being dominated by this. So this is what's going to be much, much bigger, so I can pretty much forget these and just focus on this term. So that's sort of how we're collapsing the Taylor series into this. Okay, now what exactly does this big O mean? There's sort of an informal way, which I think is a nice way to sort of remember it. If you say that a function is order epsilon squared, then that means that function is at most a constant times epsilon squared when epsilon is close to 0. So I guess you can think about it like you have some function, and you're saying that, and this is maybe, let me draw an axis here. This is epsilon, and you're saying that there's some quadratic, maybe I'll, like this, that this is c times epsilon squared for some c. You're allowed to scale it as you wish. So as I scale that, quadratic goes up and down, but it basically says I need that my crazy function is sort of being squashed in this quadratic way as epsilon goes to 0. The function is at most a constant times epsilon squared as epsilon goes to 0. So, and there's a formal definition if you're used to taking classes like analysis classes in the math department, and you want to write this in a very official way, you would say there exists constants, positive constants c and delta, such that the function you're analyzing, g epsilon, is less than or equal to c times epsilon squared for all epsilon, or all, absolute value of epsilon between 0 and delta. So it's basically saying you can always find some delta such that between there and 0 in this interval, your function g is always being dominated by this scaled quadratic. Okay, so it's sort of a mouthful, but that's why this is probably a nice way to think about it. Just at most a constant times epsilon squared for small enough epsilon. Okay, so that allows us, as we said, to take this possibly really complicated function and write it as a constant, a linear term, and then all this other stuff, which is basically quadratic. Okay, that's the whole point of this. Okay, any questions on that idea before we move on? Okay, the next step is to approximate this. So we're changing the equals to an approximate equals by getting rid of just dropping the last term. So we're saying j is approximately equal to the constant plus the slope times the deviation, and that's it. So here's a picture. Maybe j is the blue curve, and if this is W naught is my reference point, I'm trying to approximate j in the neighborhood of W naught, and I'm saying I can do that pretty well by this red curve, which is linear. So there's a slope right here. That's dj dw evaluated at this point. And the red line is chosen to have exactly that slope. And it passes exactly, it touches the function right there because we're adding this constant, this sort of offset here. So notice like when w equals W naught, this goes away and you have this, and then you have an exact match. But as w varies away from W naught, you start to build up a little bit of error. Not much error when you're close to W naught, but as W naught, as W gets far from W naught, you have maybe a lot of error. So this is just a way to approximate things by a linear function in the neighborhood of W naught. And this is going to be a really important tool for us. We're going to be able to use this over and over again. In terms of notation, sometimes we use a prime to describe derivatives. So really this is nothing more than j prime evaluated at W naught. It's a slope at W naught. But that's essentially what we're doing. When we talk about first order approximations, first order Taylor approximation, it's exactly this. So this is the scalar case. This is very easy to visualize. We're going to generalize this to vectors and matrices. But before we do that, I want to make sure that everybody is on the same page with regard to this.
I guess I just want to back up for a minute.
Sure.
Like the big picture.
Yeah.
Right. So we define j as a cost function, loss function.
Yeah. So
right?
for example, we've
So-
seen RSS.
Yeah.
We've also seen logistic loss or cross entropy, binary cross entropy, and so on. So those are examples of J's that we've seen that we're interested in finding the parameter vectors W to minimize. So in a simple, really simple case, you would just have one parameter to optimize based on your training data, and that would be like this. More generally, we have several weights, several betas or several W's to optimize for maximum likelihood. And we might even have a matrix in the case where you have several, multiple target dimensions. So that's kind of what we're doing. We're trying to figure out strategies to do that optimization. And all the strategies we're going to look at involve gradients. And so we're trying to understand gradients, what they are, how they can be used. And this is just, this little linear approximation is a tool that we'll use several times in trying to understand and apply gradients. So just like a little idea. And I think as an idea, I think it's things everybody has seen before, where you have a function and you approximate it by a line in the neighborhood of that function, right? So we're just putting some equations to these ideas.
And then the primary motivation is because this particular j is not something that has a closed form.
Yeah, the J's that we often see in machine learning are complicated enough that we can't just write down the optimal solution. RSS was really the only one you can do that with. Anything else you can't. Yeah, exactly. Okay, and this linear approximation is super easy because, as we've seen, if you have a linear model, it's often really easy to deal with, right? So linearity makes a lot of things tractable. So you're taking this complicated j and you're rewriting it as a function that depends linearly on w. And once you have that simple function, you know, this line or maybe a plane, or it's something that's, we can all of a sudden do analysis in closed form on paper and so on. Okay, good. So any other questions on any of these ideas? Two important equations, I guess. Okay. All right. So let's repeat the same thing, but now for vector input functions. And I'll try to convince you that it's really, on a kind of intuitive level, it's not really any different. The only thing we need to change is the linear term, which used to have one term like this. Now it has a sum over all the different coefficients in W. So if this has d dimensions, we're going to have a sum over d different, a sum with d terms. And the dth term will involve the partial derivative of j with respect to wj. So partial derivative of the first, of the second, and so on. Otherwise, this looks identical to what we saw on the last page, right? So it's just, yeah. It's, and I guess visually you can think about this as the line, sort of a linear approximation that you're going to apply to the jth coefficient in this vector. And you're going to do a linear approximation for each of those. And what you're going to get in the Taylor series, and there's going to be a crazy amount of terms at higher orders and all the cross terms, but we're just going to squash them all down to a sum of squares, right? That's what this is. This is a sum, again, over the dimensions of wj minus the reference w naught j squared. That's all this Euclidean norm is. So again, it's the same as this, which has a single term, but now we just have a sum of them. And that's sitting inside the big O like before. So it basically says all those crazy higher order cross terms, we're going to squash them all down to just this 2 norm between w and w naught squared. Okay, so any questions on kind of the conceptual idea? Okay. And now the rest is just to try to relabel this, if you will, in terms of some quantities that are useful, in particular the gradient. So let's first of all take a look at this. And if you remember the definition of the gradient, this was nothing more than the jth term within the gradient vector. Right? So I'm going to express that here by putting a square bracket around the gradient vector with a sub j. That means extract the jth term out of that vector. Okay, so this turned into this. Is that idea clear? Just a notational change, but it clarifies that this is the jth term of this vector. Similarly, you can think of this as the jth term of this difference vector, w minus w naught. Okay, this is based on that. Okay, so we have sum over j of the jth term in this times the jth term of this, and nothing changed with the last one. Now that we have this, hopefully you can recognize this. If I have two vectors and I do a pointwise multiply and sum them up, that's nothing more than the dot product, right? Or the inner product. And I can write that by taking the first vector. For us, they're always going to be column vectors. I transpose it to be a row vector, and now I have row times column, and when you execute that, you pointwise multiply them, you sum them up, and you get a scalar. Right? So this is just another way of writing this. Is everybody good with that? Okay. And now there's one last step, which is to sort of interpret this. So in linear algebra, when you take, let's say, a linear algebra class that's not just about matrix computations and stuff, but like a little bit more abstract, you learn that vectors are not just lists of numbers. They're actually these kind of more general things. So like a list of numbers is one way you can make a vector, but actually a matrix within, you can make a vector space out of matrices where the elements, the vectors in the space are all matrix valued. You can make a matrix, a vector space out of functions where the different elements in the space are functions. So vector spaces are kind of a general notion. There's only a couple things you need to make a vector space. If you have a collection of objects, you need that when you sum the objects together, you get things that are still within that collection, still vectors. And when you scale any of them by a scalar, that it's still within your collection of objects, your vectors. As long as you have those two things satisfied, you can make anything out of vectors. So that's kind of sort of an abstract notion of what vectors really are in linear algebra. They're these generic things. So here, we're dealing with vectors that are lists of numbers, but later we'll think about maybe matrices as vectors too. And it turns out that when you consider these vectors, you might ask a question about how do they point relative to each other? If I have two functions and I want to ask, are these functions orthogonal to each other? Are they kind of collinear? Are they pointing in the same direction? In order to describe that, you have to have a notion of angle between generic vectors. And the inner product is exactly this thing that you use in vector spaces in linear algebra to basically tell you the relative direction of two vector objects. So when we deal with real valued vectors, the inner product is just the familiar dot product. And this is these angle brackets are typically how the inner product is written. All you do to formulate the inner product is you take that first vector, transpose the second, and that tells you this quantity. It gives you this fundamental notion of how you can define an angle between vectors. But it turns out that if I work with, let's say, functions, the question is, well, how do we do this with functions? You can't do this because transposing a function makes no sense, right? So if I switch my vector space to functions, I'm going to have to define a different inner product. If I work with complex valued vectors, it turns out that the inner product in that case, you conjugate one of these guys. So even that's a little bit different. This is what we do for real valued vectors. And as we'll see on a couple more pages, that when we deal with matrices, we're going to have to come up with a different inner product. But the point is here is just to kind of explain, when we take this step, we're just trying to interpret this A transpose B within this larger class of operations on vector spaces and calling it the inner product. And then this is going to help us see some similarities as we go from scalars to vectors to matrices and realize that they all follow the same equation just with different definitions of that inner product. Okay, but for now, you can kind of think about this as sort of just a way of notating this operation. Okay, so you have that the first order Taylor series approximation of J at some point W is J at the reference plus an inner product between the gradient of J and the deviation from the reference. That's it. This last step, we got rid of this and we changed the equal sign to an approximation. Okay, so this is going to be how we do our first order approximation of vector valued functions. Direct extension of this to vectors. Okay, good. So any questions on this before we move on? Yes.
Why did we drop the L3 norm?
We are, so at this point, so this could be like a crazy complicated function, okay? This is sort of saying we can summarize that function between these two, like a constant term, a linear term, and then a term that collects all that craziness together. And now we're saying, you know what? I don't even want to be distracted by this. I'm going to approximate it. So now this is no longer equal. They're no longer equal, but we can say like they're close when W is near W naught. So we've gone from an equality to an approximation in that step, and now we don't even have to worry about this. It's gone. So it's sort of like a way intellectually where we can simplify this complicated function and just say, you know what, I can think about that as just linear when I'm near this point, and then my life gets easier. So I can visualize, I can do all sorts of things with linear functions. Okay, Any other questions on this page? All right. So now let's try to interpret the gradient a little bit more using the tools that we've developed. So I think I told you guys about this maybe back in Unit 2 and again earlier today. The gradient tells us the direction of maximum increase and the slope of a function. So here's a nice illustration of that. So this is the function in the z direction, and this function, let's say, I guess we've been calling this like W1 and W2, but they didn't use that when they drew this function originally. But here's a sort of function of these two variables. And let's say I'm sitting at this point, and that means that the value of the function will be the height here, which is somewhere there. But now let's say that I want to move in this direction. So I'm moving in my parameter space this way. What's going to happen is on that curved function, I'm going to start to curve up. And so you might ask, well, how much, if I'm moving in this direction, how much is this curving up? That would be what's called the directional derivative. It's kind of like the slope in that direction of movement. So what we're claiming is that if you want to move in the steepest uphill direction, you should point yourself in the gradient direction here. The gradient will take you uphill in the steepest way. And not only that, but the steepness, the exact slope here, you can compute from the norm of the gradient. So let's prove that to ourselves. Okay, so this is the definition of the directional derivative. So this is the directional derivative. So I think this will be pretty familiar to you just from basic calculus. So here's my reference point. U is a direction vector. By that I mean that I'm going to scale U so that its norm is 1. So that the length of U is not important. What's important is which way it's pointing. So now I'm going to move epsilon in the U direction. Epsilon is going to be a small step. I'm going to move a tiny, this is my U direction. I'm going to move a tiny step, and I'm going to see how much has the function increased. So I'm going to look at, this is the value after the move. This is the value before the move. So this is how much I've increased vertically, and this is how much I've moved horizontally. Right? And this allows me to kind of work in this multidimensional space, but still use single-dimensional thinking, because I'm moving, just epsilon in some direction. So this is the directional derivative, and what happens to this as epsilon goes to 0? Like just in one dimension, what happens when you take this quantity with epsilon goes to 0? What do you call that? The derivative, right? So this is just looking at the derivative in the direction of u. Okay, so now what we can do is we can plug in the expression from the previous page. So this is like a perturbation of j centered at this reference point, and this is going to be how far I'm moving. So on the previous page, I would call this W. So, okay, so I want to, so this is, I'm going to plug in this expression. So if this is W, then W minus W naught is just going to be this perturbation. Right. So I'm going to write this first term as J W naught. Oh, but that's going to get canceled by this, so that's gone. And now I have left the perturbation, which is this. But we said that this part of the perturbation is just epsilon u. So that whole thing becomes that. Oh, and actually I'm going to do this without the approximation. I'm going to have this thing here. Okay, but basically this order of epsilon u squared is going to be order of epsilon squared u squared. This is a unit vector, so this just becomes order of epsilon squared. So that's why that norm disappeared. Okay, so is everybody okay with that first step there? So we used this equation to rewrite the numerator in terms of what's really important. We're not going to get distracted by all the details of this, we're going to just represent that by this big O epsilon squared. Okay, now, as we described before, let's take epsilon to 0 because that's really what we care about for the gradient. So do you notice that we can do some cancellations here? What can I do with the epsilon on the bottom? What can I cancel on the top?
The epsilon and the epsilon u. And
Yes, I can cancel this, right? This is just a linear term, so I can pull this out.
And also an epsilon and then the order of epsilon squared.
Exactly. So what do you think is going to happen
It would just be
to
order
this?
of epsilon.
Order of epsilon, exactly. So this is going to be order of epsilon squared divided by epsilon is just going to be order epsilon. Okay, so that's basically something that grows at most linearly when epsilon is close to 0. But there's one other thing I'm doing. So yeah, so this is going to give me this term here. But now I'm also going to take epsilon to 0. So this will have no epsilons in it. This will be order epsilon. What happens when I take order epsilon to 0? It goes away, right? Converges to 0. So that's gone. So now you can see that this is the directional derivative is actually this. If I look in the direction u, the amount of, the slope is this scalar quantity. Now to interpret this a little bit more clearly, we're going to, maybe complicate it for a moment, but this is what we're going to do. We're going to multiply and divide by this norm of the gradient. So clearly those cancel, right? And then we're going to divide also by the norm of u, which if you remember was 1. So you can see, hopefully you can see why these are equal. But the reason we're doing this is when we make something with that form, it's very interpretable. And it's interpretable if you remember Cauchy-Schwarz. The Cauchy-Schwarz inequality or relationship says that for any vectors a and b of equal dimension, if you look at their inner product divided by their norms, that quantity can never be greater than 1 or smaller than -1. It always lives in that range. And furthermore, it says if you want to make this quantity 1, you have to make A and B collinear. They have to be pointing in the same direction. They can have different lengths, but they have to be pointing in the same direction. So that's how you can maximize this quantity. Okay, so for us, that means that, okay, when I look at the derivative, this directional derivative in the direction u, first of all, in terms of its absolute size, it's the gradient magnitude times something that is between 1 and -1. So it can never really be larger than this, larger in an absolute sense. Also, if I'm looking for the steepest direction uphill, that means I want to maximize this. Well, that would occur when this term is 1. And the way to make that term 1 is to make u collinear with the gradient. So it's saying make u point in the same direction as the gradient, and that is going to be how you move uphill, right? So that's why I've been telling you that the nice way to interpret the gradient is its direction tells you where to go uphill. So now we can finally see this concretely using this little derivation which exploited this stuff here. Okay. Moreover, when we move in that direction, when we move in that direction, then the actual size of the gradient is exactly this. So the norm of the gradient vector tells us the maximum slope, and the direction to move for that maximum slope is the gradient itself. So that's what we learned from this little analysis, which used our big O analysis of our linear approximation. Okay, so is that sort of making sense? Okay. So we're pretty close to the end. So we can extend this idea to matrix-valued functions as well. So the only thing that changes now is we have a double sum. We look at the partial derivatives with respect to each of the individual terms in our W vector, but otherwise it's identical to what we saw in the gradient case. And the only other difference is instead of the 2 norm, we need the sum of squares over the W coefficients. That's the Frobenius norm, which we also saw back in ridge regression when our targets were vector valued. So basically, the rest is just all of this is to say, you know what, this again is nothing more than the inner product. So let's just see how that happens. So first of all, let's think of how we can write this as a matrix multiply. So this term here is nothing more than W minus W naught matrices, where we look at the ijth entry. And then this is nothing more than the gradient matrix at the ijth entry. But now to prepare for thinking about this as a matrix multiply, let's transpose it so that we can swap the j and I. We're swapping ij to ji because we've transposed it. The reason we've done this is when we look at the inner sum, we can see that this is now going to be this matrix times this matrix. That's a matrix multiply in the red brackets. And what comes out of it is we're looking at a matrix, but we're looking in particular at the jth row of the matrix that comes out and the jth column simultaneously. So we're doing a matrix multiply, focusing on the diagonal elements, and finally summing them up. Well, the sum of the diagonal elements of a matrix, that's what we call the trace. So this is really just, this is doing the trace of this matrix multiply. So that's where we get this. Now it turns out that the trace of this matrix multiply is exactly the way that you define the inner product for matrices, for real valued matrices. In other words, if you want to compare two matrices and say, are they pointing in the same direction? Are they collinear? Or are they pointing in opposite directions? Are they orthogonal? What you do is you basically plug them into this expression. Another way to think about it, maybe it's even easier, just based on this, is you take the first matrix, you do a pointwise multiply by the second matrix, and you sum up all the terms. So pointwise multiply, sum up all the terms, that's the inner product between two matrices. That tells you something about the direction they're pointing, if you will. So that we're basically learning that we have kind of a common equation that always holds for how we do our linear approximation. It always involves an inner product between the gradient and the deviation from W to its reference. So we're seeing that this is always the case. So it's kind of, again, telling us, how we can interpret this gradient. It's a quantity that is very useful for linear approximations. It's basically the key quantity for linear approximations. Okay, all right. Any questions on this? All right, and let's just quickly do this. So imagine that we start with this function of the W vector. So we're going to think about A and B as some fixed vectors. So we have A times W times B, so this is going to give us a scalar. All right, it's important that this is a scalar for us. And we're going to think of this W here. Our function is going to be parameterized by W. So we're interested in taking like a gradient of this J with respect to W. So let's see what happens if we do this. And this is a sort of process that you're going to use a lot on homeworks and so on. To deal easily with gradients of vectors and matrices, I always suggest to go back to the sum equation. So let's write this as a double sum over J. So we're going to index this way over J, index this way over K. So now you have to have a sum over J and a sum over K. That's this. And then we have AJ, BK, and in the middle, WJK. Right? It's just a way of writing this with summations. Now that we have it in terms of summations, it's very straightforward to see what the gradient is. Well, we know that if I look at the J''th row and K''th column of the gradient, that's nothing more than DJ, DW, J', K'. I'm using primes just to make sure we're not confusing the variables here with the variables we're using in the sums. So how do we do this? Well, that's easy. That's just scalar calculus, right? What is the gradient of this with respect to W, J', K'? It's just A, J', B, K'. Okay, so now I know that I have this big gradient matrix, and I'm looking at some term, and I know that that term has this form. The last step is, how do I scale back to understanding this in terms of the matrix quantity. So do you see how to get from here the full matrix expression? So this tells you for any j prime k prime entry, this is what it is. So that means that if you go down the rows of here, you're changing the j primes. You're just going through the different values of this A matrix, A vector. And if you go across the columns, you're just moving across these k primes, just moving across here. So really, when it's all said and done, you have an A vector, column vector, times a B transpose row vector. So that's the structure of the gradient matrix in this case. This is a full matrix of A times B transpose. Sometimes this is called the outer product rather than the inner product. Okay, is everybody good on this? Okay, and then the last thing is, let's do the linear approximation of this function at some point W naught. Okay, so the way we define the linear approximation is JW is J at the reference point plus the trace of the gradient transpose times the deviation. So we can plug this in like this. So now I have this quantity transposed. So to do that, we swap the order and we transpose them individually. That gives B A transpose. Now, the cool thing about the trace, this is the really nice property of the trace, is that when you have the trace of a product of matrices or vectors or whatever, you can swap them inside the trace, which is something you usually cannot do with vectors and matrices, right? You can't change their order. They're non-commutative. But when they're inside a trace, you can. So it means that we can move this B around to the end. And so when you do that, you get this. And now you have something that's a row vector, a matrix, a column, which is a scalar. So the trace of a scalar is just the scalar itself. We can drop the trace. And now we get this, and now you can see that this term will cancel this term, and we're back to here. And if you think about it, it makes sense because we did a linear approximation of a linear function. So of course it should give us exactly the function back itself. And that's what happened. So this is sort of an exercise in playing with these things, and these properties and this procedure definitely does come up again and again, so it's good to see it. So, and then the very last thing I want to say is, so here's the Python code, but there's sort of a key step here. Python broadcasting, it's this concept that we have been talking about before. How does Python deal with vectors, right? Does it multiply them, add them? Does it get the dimensions right? So super important thing with Python broadcasting is how does it deal with these outer products? So what we want to do is we want to take this times this, right? But in Python, if you just give it these two vectors, it doesn't really know that you want to do this. So there's this cool thing where you can essentially expand this vector A into a matrix by doing this colon, comma, none. This tells it, take this vector and create this object like this, where you use the original elements and you move them down here, and then you just, this none means expand the columns as many times as you need to do the next operation. So this is what's happening over here. We're trying to do this here in this code. And so we're basically making, this is, in Python, this is just like a list of numbers. We're actually telling it here, no, this is a column vector. Okay, this is a two-dimensional quantity rather than just a one-dimensional quantity. And then this B transpose, we're saying something similar. Let's make a two-dimensional quantity out of that. And what this does is it uses the original values and then just cascades as many rows onto the bottom as needed until they have the right dimensions. Here, this little picture that I stole from this document is for addition. But what we really want to do here is the same thing with multiplication. But in either cases, you need the dimensions to match. And that's essentially what we're doing. So we're using this Python broadcasting trick. These green links, as you know, they're all clickable. So if you want to see the full documentation for all this stuff, click on this green link. It's a nice NumPy document. And if you click on these nones, it shows you that function as well. But basically, we'll be using this quite a bit. This is a tricky concept, so that's why spending a little time with it. You'll definitely see this on the lab for Unit 6. That lab is kind of tricky in terms of the NumPy stuff, much trickier than earlier labs, so you'll be doing this stuff in that lab. Okay, sorry for going 10 minutes over today, but that's it, and we'll see you guys on Wednesday.